Alright, so this is the third part of the videos to give some hints for our final exam problem. Fortunately, it's been a couple weeks since I've been able to work on this, so I needed to refresh myself a little bit with my spreadsheet that I have here. And as if you'll recall, we have a load path that we created. Where it started parabolically, we hit the yield surface, we had some plasticity, and we refined this. And now this is the next part we're working on, where we take this point that we found and we bring it down to here. Now I've done a little bit of, I've done the calculations for the elastic strains. We talked about those in the previous videos. We have our alpha vector at the point where we've stopped our loading segment. We have our xi, we have our stress state, and we have our corresponding strains. And I'm writing these as tensor strains right now. It's a combination of the elastic and plastic strain increment. I have done some calculations already on the final stress state, which is coming down there here as an axial stress of 210 megapascals and zero shear stress. And based on that, it appears to be completely elastic. We are less than the yield function value of the von Mises stress of 150 megapascals. This is keeping the alpha constant, calculating our xi based on our final stress state here. And so what I'm going to do is I'm going to set up my spreadsheet where I don't have any d alpha calculation. The alpha stays constant, but I am going to increment the elastic strain state based on the stress increment. The plastic strain state will stay the same. So what I'm going to do is my final total strain state minus the elastic strain increment as I move down through here will get me to the strain state that corresponds to this location. And so what I've done right now is I have taken and I copied my first load step spreadsheet into a second load step spreadsheet, and I'm going to put in the appropriate starting stresses, the starting alpha, the starting strains, and I'm going to go through and modify this so that I only calculate the elastic strain increment and find my final strain state when I get down to this particular point right here. Right, so I'm going to take a few moments and adjust my spreadsheet so that I don't get any d alphas and I don't get any d epsilon plastic terms. So that shouldn't take too long. Let me work on that and I can show you what it looks like after that. Alright, so I think I've got it all sorted out now. Did make one or two little modifications to my original spreadsheet, and we'll talk about those in the first loading step. So let's go back to that. And some of this has to do with the way that I set my spreadsheet up to begin with. But remember, when I have here's my starting stress point, and then I've changed my sigma x, my tau xy over here by just a little bit. The step from here to here creates a d sigma, and then a d sigma helps calculate the d alpha. So it's always kind of like the lines aren't completely lined up. So what I mean by that is if I look at this line, in order to calculate the xi, I'm taking the previous target sigma minus this line's alpha vector. Alright, so I do need an additional line here for my alpha and my xi that I didn't have on line 113. Okay, that's not a huge deal. Now, the other thing that I did add is I added a calculation of the von Mises criterion into the spreadsheet so I can check to make sure that I'm about 150 megapascals, which is what I'm using for my yield stress. And I am, and it stays relatively constant as I go down through here. I think there's a little bit of rounding that's gone on. You can see that it changes just a little bit, but I think it's because of the increment. But we're still basically at 150 megapascals for my yield criterion. Okay, so that's the thing that I added to that. Now what I did then is I took my ending alpha and I copied it into my second load step. So that's this term right here. Here is my ending stress state and the xi that corresponds to that. Now, this is the copied xi right here. And then here is my yield criterion value. Let's see. This makes sense. Should be 150, but the xi should have been this sigma minus this alpha. So I can make that adjustment here real quick. And so to do that, this is grayed out. So what I did is I just showed it on this line. So this xi minus this alpha is the 150.0253, which is what I had at the end of last time. And each of these subsequent ones are as we are unloading. So the yield function value indicates that it's less than 150, so we are unloading. All right, so I copied the alpha. The alpha stays constant because this is all elastic unloading. The xi changes because the sigma changes. So I'm going down to 0 shear stress, but maintaining 210 megapascals axial normal stress, sigma x. My d sigma, except for the first increment, is constant. Partial derivatives aren't needed. The unit normal is not needed. What I did to make sure I had no update to my dV toward to my backstress, my regular backstress, we're in regular stress space, is I just set d mu equal to 0. So that keeps my d alphas equal to 0. So that makes more efficient use of my spreadsheet. And I just set my d lambda equal to 0, so I had no plastic strain increment. I'm using the same spreadsheet. I can calculate my d epsilon elastics. And then, just like we had before, now here is my starting strain state from my end of my previous calculation. And here is my elastic and plastic increment plus my previous strain state. So you see my epsilon x, y, and z are not changing. My shearing strain, these are tensor shearing strains, are changing. And they are decreasing as we go down to here. All right. So now with this strain state corresponding to this stress state, what I'm going to do is look at my next load segment. Okay, it's going to go from that point somewhere here. It's going to yield, and then we're going to go through the process again where we have a portion of this elastic and then a portion of this plastic. I'll probably call this segment 3A and segment 3B. Okay, that'll be on the next video, and we'll make that in just a moment.